the head of the remote sensing team.
Hi, I'm Head ISETS-ESCAP. I'm also the head of the GRI team.
Hello, my name is John Alawiya. I'm a deep learning and computer vision engineer.
Hello, I am Fawaz Nasser. I am a deep learning and computer vision engineer.
Hello, my name is renewable. I am GIS database and dashboard developer.
Hi, I'm Wazli. I'm a GIS analyst and quality control.
And we are SolarSight.
Over the past few years, Lebanon has faced one of the most severe economic crises in modern history. The collapse of the national economy triggered an unprecedented electricity crisis, leaving households, businesses, hospitals, schools, and critical services with only a few hours of public electricity each day. To cope, millions relied on expensive and highly polluting private diesel generators, placing an enormous financial burden on families and businesses while worsening air pollution and greenhouse gas emissions. In response, thousands of households and businesses turned to rooftop solar photovoltaic systems as an affordable and reliable alternative. What began as an emergency solution has rapidly evolved into one of the country's fastest growing sources of distributed renewable energy. But this remarkable transition has also created a new challenge. Solar installations are expanding so quickly that the government and utilities can no longer accurately monitor where they are being installed, who benefits from them, or which communities remain underserved. Without this information, it becomes difficult to plan future investments, target financial support, monitor progress towards national renewable energy goals, or ensure that the clean energy transition is equitable and inclusive. This is where SolarSight begins.
SolarSight addresses this gap by combining deep learning with Earth observation imagery to automatically detect solar panels and convert them into geospatial intelligence. Rather than relying on survey, manual mapping, or incomplete records, SolarSight identifies solar installation directly from high-resolution imagery. The detections are then processed, validated, mapped, and transformed into indicators that support planning and decision-making. The result is more than a solar panel map. It is a monitoring system that shows where solar energy is expanding, how adoption changes over time, and where access remains limited. Through an interactive dashboard, user can explore results by location, administrative unit, density, and other planning indicators, making the information more useful for governments, municipalities, utilities, researchers, and development partners. Several AI-based models have already been developed for solar panel detection, but many of them were designed for data-rich environments, places with stable electricity systems, standardized rooftops, and well-documented infrastructure. SolarSight was built for a different reality, a reality where electricity systems are fragmented, solar adoption is rapidly growing, and official records often cannot keep up. The workflow begins with high-resolution satellite imagery. But the real strength of SolarSight is in the training dataset we built from scratch. We started with around 1,000 labeled samples, then expanded the dataset through iterative training until it reached approximately around 250,000 samples. At each stage, the model improved by learning from its own mistakes.
The innovation of SolarSight is that it shifts solar energy monitoring from static reporting to a repeatable image-based intelligence system. First, it uses computer vision to detect solar panels across large areas faster and more consistently than manual mapping. Second, it creates indicators that can be updated over time, allowing institutions to monitor trends in solar adoption. Third, it connects technical infrastructure mapping with social and policy questions. This means SolarSight can help reveal not only where solar panels exist, but also where they are missing. It can show differences between wealthier and less developed areas, identify underserved communities, and support more equitable, clean energy planning. In this way, SolarSight is not only a detection model, it is a decision support framework for a more inclusive energy transition.
SolarSight is designed to be scalable and transferable because it's based on imagery and trainable deep learning models. It can be adapted to different countries, cities, rural areas, industrial zones, and agricultural landscapes. This is especially valuable for less developed countries or data-constrained regions, where official energy data may be incomplete or outdated. Related approaches have already been explored in collaboration with ESCWA for selected areas in Yemen, Jordan, Syria, and Djibouti using open-source, high spatial resolution satellite imagery. In Lebanon, the approach is being extended beyond rooftops to identify solar-powered well and agriculture-related photovoltaic systems. This is important because solar pumping can reduce diesel dependence, but it can also increase pressure on groundwater if abstraction is not monitored. SolarSight therefore connects the energy transition with agriculture, groundwater governance, resilience, and climate adaptation.
SolarSight makes solar energy access visible from space and meaningful on the ground. By combining AI, Earth observation, and geospatial decision support, it helps ensure that the clean energy transition is not only faster, but fairer, smarter, and more sustainable.